In this video, I'm going to talk about when the revenue and profit are quadratic functions. Okay, so in chapter 1, when we first introduced revenue, we saw that revenue was equal to price times quantity. And when we first saw this, price was constant, meaning it wasn't changing. It was staying the same. It was constant, regardless of the quantity sold. And the quantity sold, we call that the demand. In chapter 2, demand, Q, will be a linear function of price. And that we've actually seen before in parts of chapter 1. Like we've seen how to write equations for Q that were linear. So let's just say hypothetic, for example, that Q was something like 70 minus 3P. That's a linear function of price. So if we were to take that and plug that into this formula for revenue, so revenue equals P times Q, then what we end up with is revenue equals P times, and now substituting in the 70 minus 3P. And then if I distribute this out, we get revenue equals negative 3P squared plus 70P, and that is a quadratic. So this is a quadratic right here. So we're going to use our knowledge of quadratics to do things like find where the revenue or the profit have a max, if it's a downward facing parabola, for example, like this is. So scenarios like this, where we end up with revenue or profit being a quadratic function, they're a bit more realistic than the more simplistic stuff that we saw in chapter 1, where price was constant regardless of how much of the item was sold. All right, let's look at an example. So in this example, OfficeMax can give away 250 printers in a day. So they can give away 250 printers in a day. And at the standard price of $120, they could sell 15 printers in a day. Printers cost OfficeMax $25 each, plus $400 in fixed daily costs. In part A, we want to find the linear daily demand function as a function of unit price, P. So we want to get the demand, which is Q, and write that as a linear function of P, of price. Okay, so to do this, I know that we're going to need to get a couple of points, so we'll need to get a couple of P comma Q's. So a couple of P comma Q's, we'll need this to get 2 points so that we can write down the equation of a line. And based off of what's given to us, the second sentence tells us that when the price is $120, they sell a quantity of 15. So when the price is when the price is 120, 15 would be pretty cheap for a printer. So 120, they sell 15, a quantity of 15. That would be the demand. All right, so how do we get another point from this in terms of price corresponding to a quantity that's demanded? The answer to that is in the first sentence. The first sentence says that OfficeMax can give away 250 printers in a day. What this can give away phrase means is they could give away these printers for free. In other words, if the price was 0. So if the price was 0, the quantity that would be demanded is 250. Okay, so at first glance when we read that, like if they were giving them away for free, they would only give away 250. That seems like it might be low intuitively. Like if they were giving away printers for free, wouldn't just everyone want them? Wouldn't this number be huge? But realistically, even if OfficeMax was giving away printers for free, some people might already have a printer that they were happy with, and maybe the free printer that they were giving away wasn't that good. Maybe the OfficeMax that was doing this was super far away from where a person was living, and they might not want to go out of their way to get it. Not everyone would know also maybe about this promotional offer. So there are reasons why it might only be 250 and not a higher number. Okay, so let's use these 2 points. let's try to get our slope now. Okay, so let's write down our slope. So our slope, we would do the change in y on top, so 15 minus 250, and over the change in p-values, I guess, 120 minus 0. And simplifying this, we get negative 235 on top over 120 on bottom. Okay, and I know that the top and the bottom can both be divided by 5. If I do that, I end up with negative 47 on the top, and we end up with 24 on the bottom if we divide the top and the bottom by 5. So we got our slope, so now we're ready to write down the equation. So for the equation, I'm going to use point slope form for this. Although we could also use slope intercept form, because we actually do have the y-intercept. But just to practice using point slope form, I would get y minus one of my y coordinates. I'll use this first point, it just looks a little bit nicer. Y minus 250 equals the slope, negative 47 over 24, times x minus the x coordinate, which was 0. But remember, our variables aren't y and x here. They are, so the y is q, and x is p. So we actually have q minus 250 equals negative 47 over 24 times p minus 0. And now if we isolate for q, we get that q equals, we'll get negative 47 over 24 p, and if I add the 250, we get plus 250. And that is demand as a function of price. We've isolated demand, q, and written it in terms of p. So that means we've done it as a function of price. All right. Okay, so let's do part B of this problem now. Find the daily revenue as a function of P. Okay, so we got to begin by recalling what's our formula for the revenue. So we wrote this out at the start of the video. So the formula is that revenue equals price times quantity. So in terms of variables, this would be R equals P times Q. Okay. And so we want the P there, because it tells us to write revenue as a function of P. But we don't want Q. We want P here instead of Q. So remember that Q is the quantity sold. In other words, that's the demand. It's the quantity that's demanded. Okay, so we already have a formula for the demand, so let's go ahead and plug that in. So we get R equals P times, and our formula from the previous part was negative 47 over 24 times P plus 250. And now to simplify this a little bit, I'm going to go ahead and distribute in the P, and we get negative 47 over 24 P squared plus 250P. So we end up with that. Now that's revenue, and now we have it completely in terms of P. So I'm going to stop here. If we wanted to stop at the previous line in this factored form, we could. There wouldn't be anything wrong with that, because that would still be a perfectly okay line where you had revenue in terms of just the variable P. Okay. All right, so that's part B. Let's do the next part of this problem. Okay, now C. Let's find the daily cost as a function of P. Okay, so for the daily cost, here. So remember that our cost function is going to look something like C equals mx plus b. It's going to be something linear. And remember that the m represents the marginal cost. That's how much extra cost we get from each additional printer. And the b represents the fixed cost, because the b doesn't depend on what x actually is. So mx, this whole thing, does depend on what x is. Mx, that entire thing, is the variable cost. So in our problem, if we go up and look at it, it told us that Office Max, so printers cost them $25 each. So this is the additional cost for each extra printer. So that means this is the marginal cost. And then the fixed cost, well, it tells us that. It tells us that's 400. That is the fixed cost. So let's go ahead and write these in our equation. Okay, scroll it down, scroll it down. Okay, so we get C equals, so the marginal cost was 25 times X, and then plus B, fixed cost was 400. And I'm just going to indicate these different things. So 25, again, 25 was the marginal cost. It was just the 25. The fixed cost is just the 400. The variable cost is the MX. That's the part of the cost that depends on X. That varies depending on what X is. So the variable cost is 25X. All right. So this is cost as a function of X. We want it as a function of price. Okay, so we're probably going to have to do something with this. So notice that the X represents quantity. So I want to note a key observation about this. So note that we have another variable that we associate with quantity. We also call the quantity Q. So let's plug in Q for X. Okay, so I'm going to bubble this. So that is a really important observation here. That's going to let us rewrite the cost function in terms of the demand, in terms of Q, and ultimately in terms of P. Okay, so doing this, we get C equals 25, and X will replace that with a Q, because it represents a quantity, times 400. And now for the Q, we can plug in what our demand was. So we get C equals 25 times what was Q. Q was negative 47 over 24 times P plus 250. Okay, and that's what we get when we plug in for Q and what demand was. And then we still have this plus 400 that's at the end. Okay, so at this point we do have the cost as a function of P, but let's just distribute the 25 and let's combine like terms to make this look a little bit simpler. So if we multiply in that 25, and if I multiply the 25 times this fraction, the negative 47 over 24, I went ahead and did this ahead of time, and I get negative 1175 on the top, 24 on the bottom, times P. 25 times 250 will give me, well, and actually if I add that to the, well, actually no, let me do it in steps. 25 times 250 is 6,250, and then I still have the plus 400. And now if we combine like terms, I'm running out of room, let me do that here. We get C equals negative 1175 over 24 times P plus 6,650. And that is the cost as a function of price. All right, so now let's do one more part to this example. So finally, in part D, now let's find the price, P, that maximizes daily profit. So daily profit is capital P. It's a little bit confusing. I'll do my best to write profit as a larger P. This should be capital P, whereas price is lowercase p. Okay, so what is the maximum daily profit? So I know this problem involves profit, so let's write down our formula for profit. So I'm trying to write a capital P here. Profit equals revenue minus cost. So let's plug in for each of these. So we get profit equals, so the revenue we had earlier, negative 47 over 24, P squared plus 250 P minus our cost function. And the cost function we just got, the cost function was negative 1175 over 24 P plus 6,650. So I could simplify by distributing this negative into the parentheses. So let's do that. So we get profit equals negative 47 over 24 P squared plus 250 P. That part stays the same. distributing the negative, I get plus 1175 over 24 p, and then we get minus 6650. In fact, if I simplify this a little bit more, p equals, we get profit equals negative 47 over 24 p squared. And if you get a common denominator with the 250 and the 1175 over 24, because they're both like terms, we end up getting 7,175 over 24 times p and minus 6,650. So I'm doing the arithmetic kind of quickly because that's not really the heart of the problem. I want to spend more time talking about the concepts about how to actually maximize this profit rather than doing the arithmetic. So that's why I went through that a little bit quickly with that arithmetic. Okay, so we got this function for profit. So this is a quadratic function. So that's what I can use to determine what way my parabola is facing. So I can use a here, the leading coefficient. A is negative. A is negative, and because it's negative, we have a downward facing parabola. And this is important to justify why we have a max and not a min. So I'm really going to look for this when you do questions about this as well, that you justify why it's a max and not a min, or vice versa. So downward parabola, which means we have a max at the vertex. So let's use our vertex formula because we need to find where that max happens. So vertex formula. Okay, so for our vertex formula, normally we would write x equals negative b over 2a, because that's what the vertex formula says. But in this problem, we have a different variable here instead of x. We have the variable p. We have p instead, and this is lowercase p for price, instead of x. Because I see p here, p squared, and I see p here. So we have p instead of x. But now let's plug into this. So we get negative b, so b is 7,175 over 24, over 2 times a. A is negative 47 over 24. All right, so now let's simplify this. So when we multiply 2 by this fraction, the 2 will cancel with that 24 a little bit. And I'll be left with a 12 in the denominator here. And the 2 will leave me with a 1. Okay, so now let's divide. So we got this equals negative 7,175 over 24 times, and then when I divide by negative 47 over 12, that's the same thing as multiplying by the reciprocal. So the reciprocal is 12 over negative 47. And with this, I can cancel a little bit more. The 12 and the 24, we could divide by 12 and leave ourselves with a 1 up there and a 2 down here. So multiplying this, my negative times a negative becomes a positive. And I have 7,175 times 1 on top, which is 7,175. On the denominator, we have 2 times 47. The negative's gone away. The negative's already become a positive. So 2 times 47, that's 94. Okay, so our online homework system, Edfinity, would accept an answer in this form. So Edfinity would accept this. If we needed to write it without a calculator, we could put it in this form and it should accept it. If we needed to round this for some reason, this is what we'd end up getting. So if I plug this into a calculator, this ends up giving us about $76.32. I'll go to 5 decimal places, 979. Okay, and I put dollars there because this is what P is. This is the price that maximizes our profit. Okay, and the second part of the question was, well, now tell me the max profit. So that's the price that yields the max profit, but what is the profit itself? So if I want the profit itself, what we would do is we would take this price, so this is a price, and plug it in where lowercase p is in our profit equation. So p is here, And here, so I'm going to plug in that price. I'm actually going to plug in the fractional form into that equation. So doing that, we'd get the max profit is negative 47 over 24 times the price squared. So times 7175 over 94 squared. And the next term is 7175 over 24 times the price, which was 7175 over 94. And then finally we have minus 6,650. Okay, and if I round this, if I plug this into a calculator, this ends up being about $4,759. And I'll go to 5 decimal places again. 71298. Okay, and that is our maximum profit. All right, so now we've finished our second goal here. We've talked about how we can set up quadratic revenue and profit functions and use them to determine where things like the profit are maximized, finding the vertex of a parabola and checking that our parabola is facing in the right direction.